Welcome to G Fun Facts Online. Today, we're diving deep into the mind-bending world of quantum physics. Imagine trying to grab smoke. That's kind of what scientists face with quantum states. These are super brief moments when tiny systems show off bizarre and potentially world-changing abilities. But here's the kicker: they vanish in an instant. Recently, though, researchers have found clever ways using light and electronics to sort of freeze these quantum moments, holding them steady long enough to study and maybe even use. Let's unpack this. So what's the big deal with these fleeting quantum states? Well, think about materials called quantum materials. They have amazing properties like superconductivity, electricity flowing with zero resistance, or weird magnetic powers. But these cool tricks often only appear when you excite the material, like giving it a tiny jolt of energy. The problem? These excited states are incredibly short-lived. We're talking picoseconds. That's trillionths of a second. Poof, they're gone. It's like trying to take a super clear photo of a hummingbird's wings in mid-flight. You need an unbelievably fast camera. Studying these quantum states needs similarly fast-acting tools. This is where light, specifically super-engineered laser pulses, becomes a superhero. Imagine laser pulses lasting only femtoseconds. That's quadrillionths of a second. These can pump energy into a material, waking up its hidden quantum abilities. Then, a second, weaker probe pulse checks out what's happening. By changing the tiny gap between these pulses, scientists create a sort of stop-motion movie of the quantum action. It's called ultrafast spectroscopy, and it's shown us so much about the dance of electrons and atoms. But wait, there's more. Researchers at Harvard and the Paul Scherrer Institute recently figured out how to keep these fleeting states stable for nanoseconds. That's thousands of times longer than before. They used special laser light to tweak the symmetry of electrons in a copper oxide compound. Think of the laser as a switch, nudging electrons into a new setup where they get trapped because the symmetry won't let them easily go back. To see these stabilized states, they use something called the Swiss FEL, a super powerful X-ray laser that takes snapshots of the material's electronic structure. Scientists are also playing with chirped laser pulses, where the light's frequency changes during the pulse to create dressed states where light and atoms get coupled. Super cool stuff for controlling quantum processes. Okay, so light is awesome for poking and prodding quantum states, but electronics? They're the brains and hands of the operation, especially for things like quantum computing and sensing. First, there are quantum control electronics. These are the translators between our normal world and the quantum world of qubits, the basic units of quantum info. These electronics send out super precise electrical or magnetic pulses, usually microwaves, that tell the qubits what to do. It's like giving them instructions for a quantum algorithm. A big challenge is controlling tons of qubits at once. Imagine trying to manage millions. So scientists are developing cryogenic electronics that work in the super cold temperatures many qubits need, and even open source kits like QI-Key to make control systems smaller and cheaper. Plus, using electric fields instead of magnetic ones to control qubits is looking promising for faster, more precise control, key for silicon-based quantum computers. Then, after the quantum stuff happens, readout electronics step in. They measure the final state of the qubits. This usually means linking the qubits to a detector and then turning that quantum signal into a digital one our classical computers can understand. Getting this readout right is absolutely crucial. So, when we say quantum freeze frame, we don't mean literally stopping time. It's about making a quantum state last longer, or capturing its details at a precise moment. How do they do it? We've mentioned pump-probe spectroscopy, the quick pump laser followed by a probe. There is also coherent control. This uses carefully shaped light waves, think lasers again, to guide how a quantum system changes. By tweaking the light, scientists can influence quantum effects to stabilize a state, or even make one material act like another. Then, a bit counterintuitively, there's engineered dissipation. Usually, the environment messing with a quantum state is bad. But if you times engineer how the system interacts with its surroundings, you can guide it to a desired state and keep it there. kind of like laser cooling. Symmetry protection is what the Harvard and PSI teams used, changing the electron symmetry to trap them and extend the state's life without damaging the material. Optical tweezers are also in the toolkit. Lasers can trap and move single atoms. Researchers have even used this to create hyperentanglement by cooling atoms way down and then using lasers to control their interactions. Lastly, in quantum computing, there are stabilizer states. These are robust quantum states that are easier to work with and important for developing error correction to protect quantum information. Why go through all this trouble to control tiny, fleeting states? The payoffs could be huge. Think quantum computing. Stable qubits mean more time for calculations before things go fuzzy. This is vital for building quantum computers that can solve problems currently impossible for even our best supercomputers. Then there's quantum sensing. Quantum sensors use the supersensitivity of quantum states to measure things like magnetic fields or temperature with incredible precision. Stabilized states could lead to sensors for better medical imaging, environmental monitoring, or even searching for dark matter. Nitrogen vacancy centers in diamonds are a cool example here. In materials science, understanding and controlling these states could let us design new materials on demand. Imagine materials that switch from insulators to conductors or have custom magnetic properties. This could change electronics and energy storage. Quantum communication could give us super secure networks using quantum principles. And, of course, it's all about fundamental science. The better we can probe the quantum world, the more we learn about the basic laws of physics and discover new exotic phenomena. Now, it's not all smooth sailing. There are big hurdles. Decoherence is a major one. Quantum states are super fragile and easily disturbed by their environment. Keeping them stable is tough. Scalability is another. Controlling and reading out many qubits at once with high accuracy is a massive engineering challenge. Then there's error correction. Errors will happen in quantum computations, so we need robust ways to fix them. And finally, complexity and cost. The gear for this research, advanced lasers, cryogenic systems, is often very complex and expensive. So the quest to master the quantum realm is definitely a marathon, not a sprint. But being able to capture and control these fleeting quantum states using light and electronics is a massive leap. Scientists are constantly refining their tools, finding new types of qubits, and designing smarter control systems. This quantum freeze frame isn't just about watching the quantum world, it's about actively shaping it. It's paving the way for a future where the once elusive magic of quantum mechanics is harnessed for technologies that could transform our world. As we learn more and get better at these delicate quantum manipulations, we're set to unlock incredible new frontiers in science and engineering. Thanks for tuning in to G Fun Facts Online.